The topics that we've covered so far, which were fields and complex numbers and polynomials, were in fact introductory topics. Okay, so they were just like a collection of basic ingredients that we need in order to be able to speak the correct language and work in the right realm of things in this course. But the topic that we're starting now is in fact a core topic in this course, and it's going to be related to the very, very basic ideas of this course, namely how do we solve equations, which is kind of a good thing to know. The relation we're going to see a bit later. So we're going to start with kind of an introduction. What are matrices? How we work with them? How do we add matrices and multiply matrices and all kind of terminology related to matrices and so on. And it's going to be very, very kind of like a dictionary of terms related to matrices and how we work with them. And they may be very new to many of you. Maybe you haven't encountered a matrix ever before. And after we do that, we're going to see how they're directly related to things, to many things in this course, in particular systems of equations. So here we go. So what is a matrix? That's the first thing to know. So a matrix is a chart, you can call it a chart of elements arranged in rows and columns. So, for example, here's a matrix, A. Matrix usually come with names which are capital letters, A equals, and the notation we're usually going to use is, for the chart, we're not going to draw a square with these entries, but rather we're going to just draw some parentheses in the correct size. So here's an example of a matrix. 1, 0, pi, root 2, complex I, and negative 3. So this is a matrix which has 2 rows, 3 columns, and therefore 6 entries. That's an example of a matrix. The entries, the elements, the entries are, in this course, always going to be numbers, and they're always going to be taken from some field. In this course, either the reals or the complex numbers. So this, for example, is a matrix over C. A is a matrix, and the term we use is over C. Over C means where are the entries taken from, okay? And we know it's over C because there's an I here. So we can't say that this is just a real matrix, it's a complex matrix. Clear, everybody? Okay. In general, so this was an example, how do we denote it in general? And this might be a bit scary. In general, a matrix can have n rows and m columns, and the way we denote it, in general, we have A equals, and then we could have pretty big parentheses, if it's a big matrix, and we denote the elements by sub-indices corresponding to the row and the column. So A11 is the element sitting in the first row, that's what this one stands for, and the first column, that's what this one stands for. It's not an 11, it's a 1, 1. Sometimes you'll see a comma separating the two ones, but when these are small numbers, often it's not there. So this is A11, first row, first column. This is A12, first row, second column. A13, all the way up to A1, and we have to decide, let's say, n columns. And here, this is the second row, so it's A21, A22, A23, all the way to A2n. A3, 1, A3, 2, A3, 3, all the way to A3n. A3n sits in the third row, the nth column. And here, how far do we go? We have to decide how many rows we have. So suppose we have m of them. So it's AM1, AM2, AM3, all the way up to AMN. Okay? So this is, in general, what an abstract m by n matrix would look like. Aij is the entry. Aij is the entry in row I, column J. Okay, clear? Okay. So in our example, let's take a step back to our example. Over here, what would root 2 be in terms of the indices? So root 2 is what? It's A2, 1. So A2, 1, the element in the second row, first column, is root 2. What is A3, 2? Very good. There is no A3, 2 in this matrix because this would mean a third row and a second column, but there is no third row. So there's no A3, 2 here. What is, for example, A1, 3? First row, third column, pi. This is the entry at the 1, 3 position. Clear? Everybody good? Okay. More notation. More notation. More notation. Notation is something that's usually very genius, okay? Very useful, very bright, and took a lot of time to get to the correct notation, which is precisely does the job later on in everything in a compact and convenient way. However, notation is almost always hard to get used to. Maybe not hard, but takes time to get used to. So here's more notation. So A, if we just write A, we're saying, hey, that's a matrix. We don't know anything about it. Sometimes you want to express the fact that it has m rows and n columns. So A, m by n. That's how we read it. This is a matrix with m rows and n columns. It's an m by n matrix. Often we write, instead of writing all these entries, we just write Aij. This is again a notation for a matrix whose elements are of the form Aij. Okay? So each piece of this notation reveals some information, and we'll see gradually how we use all these various notations. This A belongs to matrices of size m by n over the complex numbers. So A belongs to, and this is the notation for the family, for the world of m by n matrices with entries in the complex numbers. Okay, good. So, and by the way, there are various notations, various different notations for this. I don't want to confuse you too much, so we'll just take this. And just one more that I want to mention, if n equals to m, so saying that n equals to m means that the number of rows and the number of columns is the same. So that, what does it mean about the matrix A? Right, it's a square matrix rather than a rectangular one. Then A belongs to, we would write m sub n by n over C or over R. But in short, you'd often see M with just one index, let's say over C. Okay, so if you see just one index here, it's an abbreviation for saying n by n. That's what this means. Okay, so we'll pick up more notation as we progress. I don't want to do too much. Okay, a couple of remarks. So one, if there are many rows or columns, we separate the row and column index by a comma. So we would write, for example, A25, comma 16. Okay, because if we only use it without the comma when both the number of rows and the number of columns are between 0 and 9, or 1 and 9, and then we can just write Aij. But if the numbers are bigger, we need to separate in order to be precise. Okay, so that's one comment. And the other comment, in this course, all entries will be either real or complex. All our matrices will be either real matrices or complex matrices. We're not going to be dealing with other fields. Remember, we mentioned that there are, for example, finite fields, those z sub n's that we discussed, and other things, not necessarily fields even, but in this course, all the matrices will be living over fields and not any fields, only these two. Okay, so that's the scope of this course. Okay, so what I want to do now is present a lot of terminology related to matrices. Okay, a lot of terminology related to matrices. And it's really kind of a dictionary. So, terminology. And this terminology is going to go with the first bits of the theory and notation and some properties, and we'll gradually build it up. So, the size of a matrix, this we already mentioned. So the size of a matrix, we denote by m times n, where m is the number of rows and n is the number of columns. So the size of a matrix is actually comprised of two numbers, m and n. Okay. A square matrix is a matrix of the form A equals a n by n, the same number of rows and columns. Okay, clear? That's a square matrix. In general, a matrix is a rectangular chart or a rectangular array of entries. Okay, so this is a very specific matrix, and we'll see that these square matrices are very useful. Okay. The main diagonal of a matrix is all the elements of the form AII, where the row index and the column index are the same. So if you look at a general matrix, here's a general matrix without labeling again all the entries, the main diagonal is going to be all those entries sitting here. This is the main diagonal. Okay? A11, A22, A33, A44, etc. Now, question? Very good question. This is precisely what I was going to say. The main diagonal is a useful notion, usually when we talk about square matrices, where it starts from the upper left-hand corner, A11, and ends precisely in the lower right-hand corner, ANN. If it's a rectangular matrix, then it's not going to end precisely at this corner because there might be more elements here or more elements here. Okay? So this notion or this term is almost always associated to square matrices. Okay? Good. The zero matrix, by definition, is a matrix with Aij equals 0 for every, remember this for every sign, upside down A, for every I and j. So it's a matrix for which all the entries are just zeros. Okay? All the entries are zeros. That's called the zero matrix. Naturally, that would be a good name for it, but we'll also see that it plays the role of zero that we're used to. Okay, so we're going to define addition of matrices, and we're going to see that when you add the zero matrix, it's just like doing nothing. Okay, so that's the zero matrix. What might be slightly more surprising is what is the identity matrix, the one matrix. So a naive guess would be it's a matrix where all the entries are just one, but that's not it. And we'll see why only later when we define multiplication. So the identity matrix is a matrix, is a square matrix, has to be square, where all diagonal entries are ones, ai equals 1, and all the off-diagonal entries, all off-diagonal, and by diagonal I mean main diagonal, all off-diagonal entries are aij equals 0 for I different than j. Okay, so it's denoted by the letter I for identity, and it's square, so it's a matrix denoted by IN. IN is the identity matrix of size n by n, and what it looks like is it's an n by n matrix with ones sitting on the diagonal and zeros in all the other places, often denoted by a big 0 here and a big 0 here, or you can just start plugging all kinds of zeros here. That might even get confusing. Okay, so that's what a identity matrix of size n by n would look like. In particular, let's say I3 is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. This is I3. It's a 3 by 3 matrix with ones on the main diagonal and 0 elsewhere. Okay? So this is the notion of the identity matrix. Next, the notion of a diagonal matrix. Diagonal matrix. So a diagonal matrix is a matrix where all off-diagonal entries are 0. But the diagonal ones are not necessarily 1, but they could be non-zero. So for example, the matrix 1, 0, 0, 0, 2, 0, 0, 0, 5. This is a diagonal matrix. Okay? It's not the identity, but all off-diagonal elements are 0. So by definition, every aij equals 0 for I different than j. When I is the same as j, it could be anything. That's a diagonal matrix. A scalar matrix is a special case of a diagonal matrix. So for example, the matrix 4, 0, 0, 0, 4, 0, 0, 0, 4. So a scalar matrix is a matrix where all the off-diagonal elements are 0. Aij equals 0 for I different than j. And aii equals some fixed scalar c for all I. Okay? Can you read through the notation? Aij, an element, has to be 0 if the row index and the column index are different. So those are off-diagonal elements, A1, 3 and A3, 2. Okay? They're always 0. The diagonal elements, A11, A22, etc., are some fixed constant C. Okay, so this is called a scalar matrix, and again, we'll see what role it plays and what role this plays, etc., when we start defining the operations on matrices. So that would be shortly. A few more terms. Okay, you of course have to go over all these names and notions and terminology and start getting used to it, because we're going to speak it, okay? We're going to talk this language, and when I say a diagonal matrix, you have to think, what is a diagonal matrix? Right, it only has non-zero elements across the diagonal, the main diagonal, okay? So here's the notion of a transpose matrix. A transpose matrix. Let me start with an example again. Example. Suppose A is the matrix 1, 2, 0, 3, 1, 1. Then A transpose is a matrix where I replace the roles of the rows and the columns. So if this one had 2 rows and 3 columns, the transpose matrix is going to have 2 rows and 3 columns. The first row is going to become the first column. The second row is going to become the second column. So is it clear what the transpose matrix is? Reversing the roles of rows and columns. Row 1 became column 1, row 2 became column 2. How do we say it specifically? So the element of A transpose, the ijth element of A transpose, is defined to be the jith element of A. So given an element of A, we take the jith element as the ijth element of the transpose. So if we want to know what A transpose, what the element, let's say 3, 2 is, this 1, 3, 2 is the 2, 3 element of the original matrix. Okay, is this definition clear? We change the roles of the rows and the columns. Is it clear that this is precisely what happened here? Good, everybody? Okay. By the way, note that if A is a matrix M by N, this implies that A transpose is a matrix N by M, right? The number of rows and the number of columns is also reversed. Okay, a symmetric matrix, is a matrix that's invariant under this transpose operation. So it's a matrix that satisfies A equals its transpose. That's a symmetric matrix, meaning that Aij has to be equal to Aji, right? If it's going to be equal to its transpose, right, it has to be square. That's true, because if it's not square, then it's not going to be the same matrix. But in addition, the 2,3 element is going to become the 3,2 element in the transpose, so they have to be equal. So for example, here's an example of a symmetric matrix. 1, 2, 3, 2, 4, 8, 3, 8, 9. The transpose of this would make the first row the first column, but they're the same to start with. The second row the second column, but they're the same. And the third row the third column. Do you see that? So this is the notion of a symmetric matrix. And in particular, it has to be square. Okay. Only a few more notions, and then we'll pause this long terminology list. So none of these are very complicated. There's nothing too sophisticated going on. It's just a whole new language, a lot of stuff to absorb, and you have to read it over again and get used to the terminology. And this is a language we're going to speak freely a lot. Okay, so what is minus A? Minus A is just a matrix where I put a minus on all the signs. So example, if A is the matrix 1, 2, 3, 4, then minus A is the matrix minus 1. Let's make it a bit more interesting. Suppose A is the matrix 1, 2, minus 3, 4. So minus A is the matrix minus 1, minus 2, 3, minus 4. I just put a minus on all the elements. That's the matrix called minus A. A matrix is called skew symmetric. Skew symmetric if it satisfies A equals not A transpose, but minus A transpose. That's the condition for being skew symmetric. Remember that symmetric over here meant that it's equal to its transpose. This was symmetric. Skew symmetric means that it equals to minus its transpose. Let's try deciphering. What does it mean? So here's an example of one. Example, the matrix 0, 7, minus 7, 0. This is skew symmetric. Why? Every element is not equal to its transpose when you reverse the role of the I and the j, the row and the column, but to minus it. So A12 is minus A21. So the transpose of this matrix, the transpose would reverse it. So if this is A, let's write it. If this is A, then A transpose would be 0, minus 7, 7, 0, right? Reversing the roles of the rows and the columns. But minus A transpose would exactly give us back A. Do you see that? Does everybody see that? Okay? So in particular, so it satisfies Aij equals minus Aj. That has to happen. But in addition, if you think of it for a minute, think of it for a bit, Aii, diagonal elements, when you transpose and you put a minus, you should get the same thing. So if this were a 5, in the transpose it would still be a 5, but when you put a minus, it would become a minus 5. It would not be the same. So the only possibility for diagonal elements is to be 0. Yes, I can say it again. If this were a 5, in the transpose, the diagonal elements don't change when you do the transpose, right? Because they were in row 1, column 1. They still are in row 1, column 1. Do you agree? So if this were a 5, in the transpose, it would still be a 5. But in minus the transpose, it would be a minus 5. And the condition is that it has to be equal minus in its transpose, and 5 and minus 5 are not equal. So this implies AII equals 0 for every I. Diagonal elements have to be 0. Okay? 2 more notions. Clear? Is this clear? Okay. Again, I'm saying this is a lot to absorb. You have to 2 more quick notions, and then you have to stop and go over it. Okay. Review it and think, and maybe draw some more examples and make sure that everything is sitting there correctly. Okay. So 2 more notions. A matrix is called upper triangular if all the elements below the diagonal are 0. So for example, here's an upper triangular matrix. A equals 1, 2, 3, 0, 4, 5, 0, 0, 6. This is an upper triangular matrix. All the elements under the diagonal have to be 0, above the diagonal, whatever you want. So how do we write it formally? Aij equals 0 for an element under the diagonal satisfies that its row number is greater than its column number. Okay, so this is A21. This is A31 and A32 for I greater than J. This is the formal way of saying that elements under the diagonal are 0. You can see why it's called upper triangular, because if you look at this triangle of elements, that's the only place in the matrix where non-zero information could exist in the entries. And finally, a lower triangular matrix, equivalently, Aij equals 0 for j greater than I. So for elements above the diagonal, and what you get is a matrix where here you may have non-zero elements, and all the elements here are 0. So is this little drawing here clear? Do you understand what I mean? And we'll often use drawings like these for intuition, just for kind of expressing ourselves in short. Okay, so these are I wanted to mention two more very short terms. A matrix with just one row, is called a row vector. So a row vector, and the formal definition of vectors will follow later in this course. So a row vector is a matrix with one row. So for example, 2, 5, 3. This is a row vector. And a column vector is a matrix with just one column. Only one column. For example, 2, 5, 3. These will also play significant roles in this course, as we will see. Okay, so this really is a very big dictionary. You have to get used to all the terminology because we're going to communicate using these words. And what I want to do in the next clip is start defining operations on matrices. When are two matrices equal? How do we add them? How do we subtract them? How do we multiply them? That's coming up next.